Starting now. Okay. Good afternoon. Welcome to the afternoon session of the Introduction to Python for Data Science. So we're going to be picking up where we started this morning. If you missed this morning's session, don't worry. The recording is going to be available on YouTube probably tomorrow. If you're joining us on YouTube in the future, then you can look just below the YouTube video and you'll find all the links that will take you to the GitHub repo, the course lecture materials. Everything that's referenced in the video is in the information about this video. So with that, we're going to get started. So I'm going to share my screen, and we are going to start with reading tabular data into data frames. So as I said, I'm going to try to pick up the pace from what we covered in the morning so we can try to cover all of the remaining material. If I start going too fast, then you just have to kind of flag me in chat or unmute yourself and kind of ask me to slow down. But I am going to make an effort to try to cover a material at a bit of a faster pace. So what we want to do in this lesson is kind of show you Pandas, show you how to import Pandas, and then show you how to use Pandas read CSV function to read in some CSV data that's stored in a tabular data format. CSV is a very, very common format for storing tabular data. And then we'll see how to get some basic information about a Pandas data frame. So here we go. Okay, so Pandas is, I guess I should, Pandas. So Pandas is the kind of canonical package for getting started with doing data analysis in Python. Been around for quite a while. Was the brainchild originally of a Python developer, I believe at Goldman Sachs, called Wes McKinney, who created it to solve a gaping hole in the Python data ecosystem at the time, which was it had no support for doing financial time series modeling. And so a lot of the functionality that he developed at Goldman Sachs to serve a purpose of doing financial time series modeling that he had in his day job, and it was open sourced, and it's kind of been blowing up ever since. There's a great book. There's a link to the book over here, Python for Data Analysis. I provide a link at the end of the day. I'll provide a link to that. It's available via the Calus library. Through their digital catalog. You can also find it online. You can get it online via O'Reilly. It's a great book. It goes through lots of real-world examples of data analysis. So we're just going to scratch the surface today. But I will put the link to Pandas so that you can have that link to go and learn more. So I guess I should put Pandas documentation just to make it a bit more. Okay, so here we go. So the first thing we need to do is we need to import Pandas. So we're going to import Pandas using an alias, so as PD. So this is the canonical import for Pandas. So once we have imported Pandas as PD, then we'll reference functionality in Pandas by calling PD dot, and then if tab completion is working on your setup, then if you hit tab, you should see a whole long list of all the things that Pandas has available. But for some reason, tab completion is still not working on my my instance. So what we're going to use is actually a file called read CSV. So if you look at the doc string for read CSV, you will notice that it is enormous. This is much different than a doc string for like the cosine function in the math library in Python. This is a completely different beast. So many options. The options have quite a lot of different kinds of use cases and explanations. So it's there's a lot going on in this function, in part because CSV files that you encounter in the wild are so messy And they often need all of these special cases just in order to get them to parse into a properly formatted data frame. So that's why there's so much complexity to this function. But if you have properly formatted CSV files, usually importing a CSV file is fairly straightforward. So we are going to import, the first thing we need to pass is this argument right here, which is a file path or a buffer. So basically, we want to pass in a file path to some CSV file that we want to load. So that's what we're gonna do. So if we go to our File Explorer and go to Introduction to Python and go to go to Notebooks. So hopefully you have your notebook created in the same directory as mine. So in the Notebooks directory is actually where you've saved your notebook, because then the path to where your notebook is and where the data lives, which is in Introduction to Python data, and that's where all of these CSV files live. So then it will be exactly the same. So in particular, we want to reference this data directory, and then we're going to load the Gapminder CSV Oceana. Oop, Gapminder, that's not right. GDP Oceana. Okay. Now, there's one other thing we have to do, which is that this is a path that is relative to our current directory. So our current directory is actually the directory where our notebook lives, which is Introduction to Python /notebooks. So you can see there is no data directory in /notebooks. To get to the data directory, we need to go up to the parent directory, which is referenced by ... and then a slash. So this path basically says go up to the parent directory, which is Introduction to Notebook or Introduction to Python, then down into data, and then to the Gapminder GDP Oceana.csv file. And so this is now a big value whose type is going to be Pandas data frame. And we are going to assign it to a variable called, I will call this Oceana df, Oceana data frame. And now if we hit Shift and Enter, then we will have our data frame. So always getting the data loaded is always the trickiest part, simply because of this path issue. You've got to get the path from your notebook, where the notebook is running, to where the data file lives right. So can I just check by a show of hands? So can you just check yes if you've managed to get the data file loaded properly? And if you want to check that the data file is loaded beyond just not getting an error, if you just do, actually, you can just list out the Oceana data frame and then evaluate the cell, and then it should print out this data right here. Okay. All right, so this part is important. So if you're stuck here, if you've not been able to get this to work, then now's a good time to make yourself known so that we can help you, or Glendon can help you. Because if you can't load the data set properly, then you're going to be a bit lost as we get on with the rest of the afternoon. Okay, not a whole lot of answers, but nobody who's saying they're stuck. So okay, so I'm just going to move right along then. So there's a call out box here about the file not found, which basically just kind of explains a little bit about making sure that your path is correct to where the data file is. Okay. So once we have our data loaded, there's a couple of other things that we can still do. So first, if you take a look at the data frame that's printed here in the notebook, there's a couple of things that are a bit weird. about it. So one, you can see on the left-hand side, you have this artificial index that's been created. So because we didn't say anything about what columns of the data set should be the index, Pandas created an index, which it was just going to create using integers starting at 0. So it's created this artificial index 0 and 1. And then along the top, we have our column headers. So country, GDP per capita, GDP, or 1952, 1957, and so on and so forth, all the way to 2007. Okay. And we can actually go, because we're running in JupyterLab, if we actually go to the data directory, we can pull up the CSV file and just directly inspect it. So we can see here that we have the headers in the top row and then followed by the data. So this data set is naturally indexed by country. So if given a country, then that uniquely determines the values in the other columns. So these, given Australia, you would then say, okay, well, these are all the GDP per capita figures for Australia in different years. So a better way to load this data set is to specify the index column. So there's a argument index call, which can either be a single column or a list of columns if it requires more than one index to index your data frame. We haven't talked about lists yet. We'll talk about those in a minute, but you can create a list with just 2 square brackets. And here I'm just going to create a list of a single value, which is going to take country. And because this is getting a little bit long, I'm just going to kind of make this into a multi-line call. So now, if we execute this cell, we get back a data frame that that looks like this. So we have now, instead of these arbitrary 0 and 1 indices, we have a country indexed, Australia, New Zealand. And then our columns, per usual. Now, if we want to get some more information about the data frame, we can use the .info method on the data frame object, or the data frame variable. And you can see some more information. So here, it tells us the number of columns. So we've got 12 total columns. The index has 2 entries, Australia to New Zealand. And then we see that here are the column names. We have a count of how many non-null, so that's basically non-missing values, are included in that column. So we see 2 non-null all the way across. So we know that there's no missing data. All the data is not null. And then we can see that these are all data type float 64. And at the bottom, we see memory usage is a little over 200 bytes. So this is not a big data frame. If you have, you're working with larger data frames, the amount of data you generally need about an order of magnitude more CPU memory than the amount of data, or the size of the data that you want to load, just as kind of a rule of thumb, in order to allow for sufficient memory overheads and things like that come from working with these kinds of libraries, just as a rule of thumb. Okay. So just some other basic things about data frames. So if we wanted to access the columns of our data frame, so there is a columns attribute. So you can get the columns as an index object. So basically, this is just the list of all the columns in the data frame. Sometimes it might make more sense to kind of, a data frame is a 2-dimensional object. So sometimes you might want to transpose it like you would a matrix. So here we have the country, Australia and New Zealand are the rows, and then the columns are kind of GDP per capita in a particular year. So kind of like a time series. Usually for time series data, it makes a little bit more sense to think of the rows as being the time dimension and the columns as being a variable dimension. So if we wanted to get a data frame with the swapped rows for columns, we could just transpose it. And that would give us a new data frame. Now, of course, here I've just transposed it and kind of displayed it in the notebook. I've not actually assigned it to any variable or anything like that. So if you wanted to store the transposed data frame like this, then you would need to assign it to another variable. So there is another method that's useful for getting at descriptive statistics. So if we do ocean data frame dot describe, so this returns another data frame that is filled with descriptive statistics. So, and by default, it's Pandas kind of computes these descriptive statistics on all of your numeric columns. So if you have like our columns up here, these were all float 64 numerical column, data type columns. So Pandas is going to compute descriptive statistics for all of those columns. If we had other columns that didn't contain numbers, they were categorical variables or ordinal encodings or strings or something, then it would just ignore those columns when computing the descriptive statistics. But here you can get the count, the mean, standard deviation, and min, max, and other quartiles. Okay. So there are some exercises. So it's important that you understand how to load data. That's like the fundamental thing of doing one of the most fundamental and sometimes difficult things of doing data analysis, just getting the data loaded. So the exercises at the end of this episode, if you want to take 5 minutes just to kind of go through those, then I can take questions. So there is an exercise on reading and other data sets. So GDP for the Americas, just as an example. Introducing some new methods, a head method and a tail method, and for inspecting data frames and try to figure out what those do. And then this one is more, do you understand the concept of relative paths and how to point your analysis notebook at your field data microbes.csv? And then also we've looked at a read CSV function. There's also a toCSV function, which will take a data frame and write it out to memory as a CSV. Write it out to disk as a CSV file. Okay. Good question. So in the chat, there's a question about why column doesn't need parentheses, but info does. And the difference, it's a bit of a subtle difference that has to do with the fact that columns is an attribute, and info is a method, and needs. So a method is kind of like a function, and we're going to talk about defining our own functions, but methods are special functions that are attached to certain data types. And sometimes they take like functions, sometimes functions take arguments and sometimes they don't. Sometimes methods take arguments and sometimes they don't. So this is an example of a method that doesn't take any arguments. And then there are things like attributes, which are basically accessing individual bits of data about the data type itself. In this case, we're just accessing a representation of the columns of the data frame. So it's an attribute and doesn't require parents. If my tab completion was working, I could give you a better, more visual understanding of the two. So if you hit tab and then you look at the listings of things that you can do with the data frame, the tab completion will tell you which ones are methods and which ones are attributes, basically. But unfortunately, my tab completion does not seem to be working. Yes, so shape should also be an attribute. So, so there's a question about shape. So the shape is just going to give you the number of rows and the number of columns in the data frame. And so it is an attribute, and if you did something like this, you'd probably get an error. Yeah. So I'll just put this shape returns. So is an attribute that returns in rows in columns. Okay. Okay, I realize I've left my timer, meaning my phone, in another room. So I am going to go and fetch it. And in the meantime, you guys go ahead and work on these exercises. And then I'll be right back, and then I'll answer any questions that you might have. Okay, I'm back. Does anybody have any questions about what we've covered there in the reading data? Oh, forgot to set the timer. Okay, so the CSV file, so there's a question in chat about where do you find the CSV file. So let me share my screen again. Okay. So the CSV files, the data files, are stored in Introduction to Python data. So all the CSV files are here. Now, you need to get the data to load, you need to provide the path to the data file into the read CSV function. But the path needs to point from where your notebook is stored. So here, and I'm hoping that you've been following along with me and placed your notebooks in the notebooks directory. So if you've placed your notebook in the notebook directory, then you can just type the path that I have here. Now, I think the lecture notes might assume that you have the notebook, not in the notebooks directory, but somewhere else. So Abdul Rahman, so yes, thank you. So that the link that you provided would be if you want to get the data to download locally, then you could get the data from there. But that's not going to help you because you're downloading the data files locally to your laptop is not going to help you the data is already in the cloud, so you don't have to download them or anything. Ah, I see. Okay. Well, if you're using Python on your Mac, then yes, you'll have to download the data files locally. So there's a question. So is it okay to apply two methods simultaneously on the same variable? So simultaneously is doing quite a lot of work in that sentence. So what exactly do you mean by simultaneously?
I mean, for example, we transpose and then we describe the data, or.
Ah, I see. So that's called method chaining, because what you're doing is you're really doing each of those one after the other. So you're not doing them simultaneous. You're doing them in sequence. So and we'll see lots of examples of method chaining. So for example, if we have our Oceania data frame, and then we do something like this, and then we do something like this. So what is really going on here is, first, this transpose is being applied, and then the describe is being called on the result. If you want to be very explicit with but that's a technique that's called method chaining, and it's used quite a lot in Python. And in fact, as we build up longer and longer kind of computations with pandas, we're going to see that I'm going to start doing method chaining like this, where I just line everything up on the small example of method chaining. So where method chaining is really useful is where you don't care about these intermediate data frames. So we don't want to store the results of the transpose. We just want to take the transpose and then compute the descriptive statistics for it. So this avoids kind of storing all these intermediate results, basically, that we don't really need. Good question. Okay. So everybody was able to get now's kind of the last chance if you're stuck on getting the data set to load, because you'll have trouble with the rest of the material if you can't get the data set to load. So anybody who is stuck with getting the data set to load, just go ahead and check no in the participant section, and I'll open up a breakout room for Glendon to come in and get you unstuck. Okay, so we've got a couple. So Glendon, I'm going to open a breakout room.
Cool, awesome.
So there's a couple of questions. So there's some people with issues loading data, some people with module not found error, no module named Pandas. That must mean that they're not running in the cloud, but somewhere else.
Okay.
But okay, so
I see 3 people, Daria as well.
Yep. I'm going to create the room. And then assign Glendon, Daria, and okay, so those of you who have either asked in chat that you've got an error or have made yourself known to the participants, you should get a little invite to go and join the breakout room. and Glendon will be there with you to try to help you. Okay. And we'll see you all back in a little bit. Okay. So for everyone else, we're going to go ahead and move along. Right, so we talked about how to load data. We saw how to specify an index column when you're reading in a CSV file. Usually, all CSV files will have a proper index, not that you can use to pass into the index column when you're loading the data. And we saw some basic methods and a couple of attributes just to get started. Okay, so we're going to move along to the next episode. Okay, so now we're going to get into kind of Pandas proper. And so we're going to talk about doing statistical analysis on tabular data. And in particular, we're going to cover a lot of different ways to subset data in Pandas, how to extract individual rows, individual columns, subsets of rows and columns, how to use Boolean conditions to index data, things like this. Okay. Okay, so there are quite a few ways to select subsets of data in Pandas. So first, we're going to get some more data to work with. So since the Oceania data frame only has 2 rows, we're going to get something that's a little bit bigger. So we will do, we'll load the data set for Europe, the same data set for Europe. So we're going to do Pandas, read CSV, and then the path from our directory where the notebooks are running to where the data file lives, gapminder, gapminder Europe, gapminder GDP Europe, CSV. And again, for the index column, country. Okay, so let's take a look. So this data set has quite a bit more countries, covers the same period of time, with GDP per capita statistics from 1952 to 2007. So same kind of time range, but for a larger number of countries. So I guess I should mention, so GDP per capita, so GDP is a measure of economic output in a particular country. GDP per capita is that measure of economic output divided by the number of people alive in that country in that year. So that's GDP per capita. Now there's some subtleties with comparing GDP per capita across countries and across time. And one issue is that, I think these are measured in US dollars. So a US dollar in Albania is a lot different than a US dollar in the UK, for example. So a US dollar will buy you a lot more in Albania than it will buy you in the United Kingdom. So there's differences in what are called purchasing power across countries. And so that the GDP per capita figures have been adjusted to take into account the purchasing power differentials in different countries. And then also you can have inflation or deflation, where the value of currency in a country changes over time. So, a dollar today is worth a lot less in general than a dollar, 20 or 30 years ago in most countries. So these GDP per capita figures have been properly adjusted so that we can do rigorous statistical comparisons across countries at the same year, but also within a country across time as well. So I probably should have mentioned that just in case anyone was unfamiliar with GDP and GDP per capita and these issues. So, this data has been properly takes that into account. So, but we want to talk about subsetting data. So let's suppose we wanted to select out this data value, just this one data value right here, just to start. So the value of GDP per capita in 1952 in Albania. So how might we do that? Well, there is a method called iloc on the data frame. And with iloc is basically allows you to do indexing, integer-based indexing into the data frame. So the 0th row and the 0th column. Whoops, what did I call this? Europe. Let's call it Europe data frame instead. Okay. And just because this is a pretty big data frame, in one of the previous exercises in the last episode, they talked about this head method, which prints out the first, by default, I think 5 rows in a data frame. And you can control that by specifying a value n, which by default is 5. There we go. So you can see that using iloc, we can do integer-based indexing into the data frame. And this allows us to select off the 0th row and the 0th column value, which is this value of GDP per capita in Albania in 1952. Okay. However, integer-based indexing makes sense for things like arrays, but it makes a lot less sense for things like data frames. Data frames have, there's not really necessarily an inherent ordering to the rows or to the columns of a data frame. So like, why would you want to index based on integer indices? A much more sensible way to index with data frames is to take advantage of the fact that data frames are labeled. The rows have labels, the columns have labels. So why don't we use the labels for indexing? And we can do that instead of iloc, if we just use the loc method. And this allows us to do label-based indexing. So for example, we could select the same value by specifying the row label, Albania, and the column label. And that gives us the exact same data. So in general, I would never, don't do this. You should always prefer label-based indexing with data frames. Okay. Now, but generally, we're not really interested when we talk about subsetting data. Usually, we're interested in either selecting, all of the rows for a given set of columns, or all of the columns for a given set of rows. We're usually not interested in just selecting out a single specific value. It's too specific. So, if instead we wanted to select the entire time series of GDP per capita for Albania, we would just use a single colon. And so the colon, just like when we were indexing strings earlier, the colon stands in for a start, stop, step kind of syntax. But if we don't specify the start and the stop, the colon is just going to say select everything. So if we do this, then we get back a time series, basically, of GDP per capita in Albania. And actually, you don't necessarily need to provide the colon. You can actually leave it off. Okay. Glendon, I see you're back, or are we all?
I'm back and it's all ready to go again.
All sorted. Okay, excellent. Thank you very much.
And
So for those,
I'll be gone for an hour. So.
Okay. All right. Bye-bye. Thank you very much. See you again later, maybe.
Thanks.
Right. Okay. So for those of you just joining us again, so we just picked up in Pandas data frames, we loaded a data frame for Europe. So we've just loaded the data frame for Europe, and we've just been going through talking about some ways to index. And the lecture notes talk about 2 different ways to do indexing: integer-based indexing with iloc. And I said, you can do that, but you don't really want to do that, so don't. And then instead, you should use this label-based indexing. And so we're basically just talking about label-based indexing now. Okay, so that was kind of a time series of selecting data across for a particular row, all the columns. But what if we wanted to select all of the rows for a particular column? So in this case, that would be like 1952. In this case, that would be like a cross section. So you're saying at a particular point in time, so 1952, what is the GDP per capita across all the countries in Europe? So this would be like, for example, if you wanted to do a distribution of this variable at a particular point in time, then you would do something like this. So you would select that out, and then maybe you would plot a distribution of that. And we'll talk about plotting, but just to kind of give you a hint of things to come, you could do something like kind. Oh, I didn't install SciPy. I will install SciPy later, so that if you come back and try this, it will work. I didn't realize that I did not install SciPy. So to do, install SciPy. Righto. Actually, you know what we can do? We can install that now. This would be a good. So what we can do is we should be able to go ahead and install SciPy right now. So this is a bit out of scope, but there's actually a magic command called conda, which you can use to install packages. And installs package inside the Python kernel in which the notebook is running. Hopefully this is not going to take very long. But I will make a note to myself. I'll open an issue on this repository for the course and install SciPy so that the KDE plot will work properly. So this is actually a little bit of an aside from what I had intended to do. Still installing. I don't think I want to wait for this. So I am going to stop it. Okay. So I'm just going to go ahead and stop that. It was taking too long. So we'll have to make do with a histogram. So this would be an example, and we'll see some more plotting examples later. And I will go back and install SciPy so that it will work. In fact, maybe I should just show you how to do it now. So just because, so this is something that we talked about, or that was covered in the Conda lesson earlier that we didn't go through in much detail. But what I can do is I can actually come here to the environment.yaml, and then I will add, actually edit this file, and I'm just going to put, come down here and put SciPy. And I'm not sure what the most recent version of SciPy is. So I will do a new terminal, and I will go and find out what the new, or what the most recent version of SciPy is. So this is kind of an example of a workflow that if I was prototyping something, you know, I'm working along in a notebook, and I get to the point where I have this this functionality that I want. Like I really want to have SciPy installed properly so that I can do the KDE plot that I want. So I need to install it. Oh, there's a really big lag in my Conda search SciPy. So this Conda search command is going to go and tell me what versions of SciPy are available. Okay, looks like 1.5.2. So go back here, and I will just put 1.5, and then added SciPy. And I will commit the changes. Okay, so now the next time somebody comes along and happens to click one of these buttons, then Binder will rebuild the entire infrastructure for this repository and install SciPy, and then SciPy will be available for people who come along later. So now that that's done, I'm just going to let this work in the background while we go and do other things. So we'll come back to that maybe in a little bit. Okay. Hopefully that was an interesting aside to kind of show you how I would debug a workflow where I needed to install something that wasn't installed, which happens not infrequently. Okay, so we've done some label-based indexing where we selected all the columns for a particular row and all the rows for a particular column. But what if we want only some rows and only some columns? Well, again, we're going to use the labeled data, labeled indexing, label-based indexing. And now we can look here and we can say, okay, well, let's suppose we want to start at Italy. And then go up to and including, in this case, I don't know, Portugal. So let's take a look and see what this does. So this gives us Italy up to and including Portugal. And then of course all the rows. So if we only wanted, or all the columns rather, if we only wanted some of the columns, then we would need to put restrictions on the labels in those columns. So if we only wanted 1967 to 1997, then we would do like this. And so that's an example of how to put restrictions on both the rows and the columns. So we can use the results of these like subsets, you can use them in further computation. So you could either do something like this, where you call this, you could assign the value of this subset call to a variable, and then you could do something on the variable like compute the max. So this computes the max across one dimension of the data frame. So it computes the max across the rows by default. So there's an argument in here called axis, and by default the value is 0, which corresponds to the rows. And then if you set axis equals 1, that would compute the max applied across all the columns. So in this case, this would be the max per capita GDP for Italy in any of those years. And then the other way it would be picking out the GDP per capita that was the max in that year. So probably Norway for most of those years, or all of those years. Yeah, so this is the same as Norway. But or what I would probably do is, because we don't really care about this intermediate subset data frame, is I would do method chaining. And notice that I have to enclose the whole thing in parentheses, otherwise Python will complain. It'll give you a syntax error. So you need to put the whole thing in parentheses, and then you'll get the same area. So this is same result as above, but with method chaining. Okay, so now I've come back just to check on this installation, and it was waiting for me to say yes, it was okay to install SciPy, so I said yes. And now we're, or I guess more specifically, I hit Y for yes and then hit enter, and then now it's installing. And now it's done. So I think.
So I have a question here.
Yes.
After the max, you put some extra information. In the last. Axis equals 0. What do you mean by that?
Sure. So right. Okay. So let me just, before I come back to that. So notice that this this kind, I tried to do KDE for kernel density estimator originally, and it didn't work because it said SciPy wasn't installed. So then I showed you kind of how we would solve that problem, and then SciPy has finished installing over here. And so when I came back and changed this to KDE and then reran this cell again, it created the plot, but then instead of using a histogram, it did some kernel density estimation to smooth the values and give a distribution of another way to estimate the distribution of GDP per capita in 1952. Okay, now back to your question. So, okay. So if you're going to compute the max of, let's just leave this out. So if you're going to compute the max of a data frame, you have to decide like, okay, well, which dimension do you want to compute the max? Do you basically want to compute the max, the per column max? So basically the max across the rows. So do I want to go in like 1967, what was the max value of all of these GDP per capita values? And similarly for 1972, 77, 82. Or do I want to look at each row and say, well, what is the max of all the GDP per capita values in Italy across all of these different years? So depending on what you want to do, you have to specify one or the other axis. So by default, the axis for these kinds of calculations, the default is always to look across rows. So basically for each column, it will compute the max across rows, or the min across rows, or the mean across rows. And so that's axis 0. If you wanted to do across the other axis, then you need to do axis equals 1, which will do axis across for each row, it will compute the max across all the columns, or the min across all the columns. And you can have higher dimensional data, but that's outside the scope of our discussion today. Does that make sense?
Yeah, it's clear now. But is there a way to include the country name?
What do you mean? So,
like, for example, the GDP per capita at 1967 is 16,000 something, but it belongs to which country? That's my question.
Ah, I see. I see.
Yeah, I believe there is a trick or somehow like.
So what you want is to actually select out Okay, so let me see if I can experiment a little bit on how to do this. So one of the things when you're doing data analysis to realize is that there are often more than one answer. There's more than one way to get the result that you want. And so I might come up with something here.
You can, for example, find the location of that result and then shift it by one column to the left.
Well, so what the this is hard to do when your tab completion is not working.
I think you have to import NumPy to use argmax.
Well, so Pandas is built on top of NumPy. And so Pandas actually, like NumPy is already installed because Pandas uses NumPy as a dependency. So all of that is there. But I feel like there is, oh, okay. So it's not on a data frame, it's on a, so then something like, all rows and then GDP per cap in 1952, argmax. Rows. Oh, because there is no 1952 in the subset data frame, because we started the subset at 57. Okay. So, and then if we did, okay. So what you could do, this would be a really, really inelegant way to do this, and uses some things that we haven't necessarily talked about yet. But if you really wanted to do something like this, you could do And then we could call this I'm not sure if this is going to be a great learning outcome for you guys or not. So what I did here, and we'll talk about for loops later this afternoon, but I looped over the columns and basically picked out I'll call this richest country. And the way that I did this, richest country index, so to get the richest country, the label, I found the row that contained the richest countries, the richest country. And then from the index, which just contains the names of the countries. So first I went through each column and I said, well, where's the max value? Well, in 1967, it's this value here is the largest. Well, what integer index is that? Well, 0, 1, 2, 3, okay. And then I went over here to the country list and I said, well, which country is the third country? Well, Italy, 0, 1, 2, 3, Norway. And then I did the same thing in 1972, Norway again, 1977, Norway again. And so basically, that little loop basically just goes through and picks out Norway in every. Now, I am 100% certain that if I were to look through the documentation, that there is a much better way to do this that avoids this for loop and all of this mess. But I just can't think of it off the top of my head. And because my tab completion is not working, it's hard for me to search through the documentation efficiently. So that's as far as I'm going to be able to take this one. Okay. So where does that leave us off? Okay. So next thing, so comparisons to select data based on a value. Okay, so we have our, so we're going to work with this data frame. So what if, so we're going to do some comparisons. So what if we take this and when we do, well, greater than 10,000. So this does an element-wise comparison. So it compares basically the value of data in the data frame in each position with this value that I've given here, 10,000, and then said, is that value greater than 10,000? If yes, it'll be a true. If not, it'll be false. And so this gives us what's called a Boolean mask. We're using a condition, a Boolean condition, a true or false condition to mask values depending on whether they are true or false. So now what we can do is we can actually use this as a condition. So I'll call this is greater than 10K. So we can actually store this result as a variable. And now if we wanted to look at, whoops, so this should be Europe data frame. And now if we wanted to look at we can use this indexing notation to, maybe 10,000 was a bit extreme. Oh, no, sorry. I know what I want to do. So I actually wanted to, let's store, let's do it like this. Okay. Now, if I want to do, we've got too much data, it's hard to look at. There we go, that's a little better. So you can see, so what we've done here is we've selected out some subset of rows and subset of columns. And then we said, okay, well, let's set a further condition on whether the GDP in that country in a particular year is greater than, say, 10,000 US dollars. And then we stored that as a data frame. But then we can actually subset a data frame with another data frame. And then this has the result is that it will, so let's just look at this. Okay, so here's the original data frame. So we have GDP per capita in a particular year in a particular country for some subset of countries and subset of years. Then we ask, well, when is this value greater than 10,000? And so then we get this data frame, which includes only trues or falses. And then we can use this kind of square bracket indexing syntax to kind of mask out the values in the subset data frame for where that condition is false and replace them with not a number. So you can use this use this kind of masking idea to remove data that you no longer want to continue analyzing, basically. So now, for example, if we did descriptive statistics on this, you can see here the descriptive statistics are now computed on values where they've ignored the NA values, the not a number values. So that's why you can see the count of non-null values is 3, because there are 1, 2, 3 non-null values in this column. And similarly, 3 and then 4 and then 5, 5, 4, 5. So that's another interesting way to kind of subset out data in Pandas. Okay, so looks like we might have some things in the chat. Index max. So thank you out there. I should have checked on that a few minutes ago. So then up here, instead of this, there should be subset data frame. See, I knew there was a okay. Thank you, Athir, for bringing that up. So this is a great teaching example. Okay, so this is the solution that I hacked together without reading the docs. Yeah. This is the best way to do the same thing from reading the docs. And this actually gives you more, because this we would have to actually cast into a data frame, and this is just a list. And so this is a great teaching example, and that read the documentation. So if you find yourself, particularly when you're getting started with a new library, and you find yourself writing code that looks like this, you should stop and you should think, you know what? There is probably a better way to do this. Someone else has probably had the same problem that I'm trying to solve, and they've already solved it. So I'm going to go to Google, I'm going to go to Stack Overflow, and I'm going to read the documentation for the library that I'm using and try to figure out whether or not something already exists that does what I want. And 90% of the time, you're going to find that that is true, as is the case here. There was already a function that did exactly what Abdul Rahman wanted. Okay, thank you. Okay, so now we're going to take a look at group by. So we covered all of this, group by, split, apply, combine. Okay. So in Pandas, well, not just in Pandas. So in data analysis in general, particularly when you're working with tabular data, a common pattern of data analysis is to, you have a whole bunch of data. You're going to group the data into bins according to some definition of what it means to be in a particular bin. And then once you've binned the data into these different groups, you're then going to compute statistics on the samples that you've grouped into each bin, whether it's grouping by some characteristic of the data and then computing means or maxes or mins or some arbitrary function. So that's what split, apply, combine. So basically you split the data into bins, or you group it into bins, you apply some transformation to the data, and then you combine the result back into a final data frame. And so there's a kind of a concocted example here of how we might do that. But this is a very generic kind of data analysis paradigm that comes up a lot, not just in Python, but in R, any real language for doing data analysis. And it's highly, very much related to the workshop that I taught last week on SQL. So SQL is called structured query language. It's a query language for extracting data from relational databases. It's kind of the forefather to all of modern data analysis because so much of the world's data is stored in relational databases. And so a lot of libraries, whether they're in Python or R or some other language, have been heavily influenced by SQL data analysis semantics. So that's a bit of a plug to kind of go back and maybe take a look at the SQL workshop from last week, because it covers a lot of general ideas for data analysis that you'll see again and again in other areas like Python and R and other places. Okay, so let's go through this group by, split, apply, combine. Okay, so let's start with, we have our European data frame. And what we want to do is we want to bin European countries into groups depending on how relatively wealthy they are. So we want to come up with some definition of what it means to be wealthy. And then we want to put kind of maybe really wealthy countries in one bin and really poor countries in another bin, and maybe kind of middle income countries in another bin. And I don't know, maybe we'll have 3 bins, or maybe we'll have more bins, and we'll see. But we kind of want to group countries that are have the same kind of relative levels of wealth into one bin, and then compute statistics for those groups within each bin. So if we start with our full data frame, we need to come up with some definition of what it means to be wealthy. Well, so we can compute the mean across the rows. So this is going to compute for each year in the data set, for each column, it's going to compute the average GDP per capita across all the countries in Europe in that year. Yeah. Okay. Now, what we could do then is we could say, okay, well, let's compare yeah. So let's compare. I'm going to try to set this up so that you can see the comparing visually, and then I'll explain what's going on. So if we look at the first few rows of okay. Right, so this kind of works. So what's going on here is, okay, so we have I'm just going to transpose that. No. Trying to get all this to fit. Okay, I might have to do it like this. So let's take Albania in 1952. So Albania in 1952 had about $1,600 US GDP per capita. The average across all countries in Europe in 1952 was about $5,600. So Albania, greater than GDP per capita in 1952, should be false. And indeed, we see that it's false. Now let's look at Austria. So Austria had a GDP per capita in 1952 of $6,100. That is greater than $5,600, so that should be true. And similarly for Belgium, it should be true. Bosnia, it's false. And so what's going on here is Pandas is smart enough to align labels. So it basically has taken these labeled 1952, and then when you run this comparison, it basically aligns the labels so that it's comparing GDP per capita in 1952, the average, with each of these values in 1952, and then the same for the other years. So if we picked, so in 2007, the GDP per capita on average was $2,500 US. So then if we look over here at, so neither, so Albania is still less than average. Austria and Belgium are greater than average. Bosnia is still less than average. And then who is this? Bulgaria is also less than average. And so if we were to go over here, we would see false, true, true, false, false. So, which is exactly, so Austria and Belgium were still relatively wealthy. Okay, so that's, hopefully you can understand now kind of what this is doing. So just like we stored, this Boolean condition, which returns a true false, a data frame which is filled with trues and falses, we're going to call this, so is relatively wealthy. Yeah, so we'll call this is relatively wealthy. And now what we have is, so we have this, this data frame is relatively wealthy. And if we computed, so trues and falses can also be thought of as zeros and ones. So if we did something like is relatively wealthy, and we did the sum across all the rows, well, or let's do it this way. So no, if we did the sum across all the columns, what would this count? So it would count the number of times for which, say, Albania had a GDP per capita that was higher than the European average in that year. So we kind of glance across here, we see, okay, well, Albania is a fairly poor country, and so it never has GDP higher than the average in any year. So let's spot check another country like Switzerland or something, a wealthy country, Switzerland. So this probably should be true in every year in the data set. Yes. Same with the UK. In a country like Germany, also relatively wealthy, although in 1952, Germany was recovering from the Second World War, and so not necessarily very well, not so wealthy. So if we sum across the rows, sorry, across the columns, then we get these counts. And if we wanted to, we could actually normalize these. So instead of the sum, we could use the mean. And so now, what has this done? It's given us, well, actually, either the sum or the mean we could use. But this has given us a way to group the countries. So countries that are always wealthier than average, those are like your really wealthy countries. So if every year in the data set, they are wealthier than average, and that's a really wealthy country. And so these are the countries that have ones. So this is our criteria for binning countries. So all countries with ones are going to go in the same bin. All countries with zeros are going to go into the same bin. Those are going to be the poor countries. And then you've got two other bins, so 0.5 and 1/3. And some countries are going to go into those bins. So it looks like Czech Republic and Italy, half the time they had greater than average wealth, and then Greece and Ireland are about 1/3 of the time, also Slovenia and Spain. So now that we have this score, we can group countries according to the score. So we can do Europe, group by, and now we have to pass in something that we wish to group by. So we'll call this, what do we call this? We will call this our wealth score. And I'll just put, just so we can, so you have what that, so you have what that looks like in the notebook for later. So if we group by the wealth score, so this returns a special data type called group by, but now we can do things like mean. And now this is giving us, instead of countries now, we have these bins, 0.33, 0.5, 1. And for each of these bins now, we're computing the average GDP per capita across countries within that bin in 1952, 57, 62 across time. So we did this kind of complicated calculation to get a variable that we could use to do the binning. But then once we had a variable to do the binning, we could group by that variable and then apply the mean function, and then Pandas handles the combine for us and just combines the results back into the same data frame. Okay, so that was a quite elaborate example. There's a lot going on there. So now there are a fair number of exercises. And usually at this point in the day, people are kind of both getting tired, but also have lots of questions about what we just did. So I'll set 5 minutes on the timer for the exercises at the end of the episode 8. So you can get some practice with subsetting data, some more slicing data, and I should have known about that index min and max. It's actually in an exercise down here. Somebody must have been working ahead. Yeah. Okay. So off you go to work on the exercises. Does anybody have any questions? Stop my screen sharing for a moment. Does anyone have any questions? Okay, so yes, so the session is, so just as a reminder, so just like this morning, the session is being recorded. Then will be put on the Cal's VizLab YouTube channel. So tomorrow, once I get everything loaded onto YouTube, I will send out a link with, or an email to everyone with a link to a feedback form that I'd like you to fill out for today. And along with that feedback form link, there will be a link to the Cal's YouTube channel, which will include these videos. I can give you the link to the YouTube channel now, but obviously the so I'll put the link to the YouTube channel in the chat, and it has all the videos that we've shot so far this this term, but these two videos will be up tomorrow. Okay. Okay, so while you guys are working on the videos or on the exercise, if there are no questions, I'm just going to take a short break, and I will be back in just a couple minutes. Okay, I'm back. So these exercises are a bit more involved, I think, than many of the exercises in the previous episodes, and this is kind of the first more kind of deep dive into pandas and functionality in pandas and things like that. So it's okay if you're feeling a little bit lost. Sometimes it takes a little bit of going through these exercises on your own. And now you have the recording, you can come back and watch. So Huang asks a question: is grouping by floating point numbers reliable? And it's a good question, actually. And in fact, I was thinking the same thing, that actually what I would probably do is, rather than group on the floating point numbers, and our wealth score up here, we could just actually use the sum. And if you use the sum, then you're going to get integers. And the groups will be the same. Just that the integer labels, grouping on the integer labels is probably a bit more stable, shall we say. So that's a good question. Or not so much a question as a point. Okay, anything else before we move on? Okay, so the next episode that we're going to cover is some plotting. So you've already, I showed you a couple quick examples of plotting, so we're going to do more of that, basically. So in this episode, we're going to talk about how to plot data and how to save plots for publishing. We'll create some time series plots and some other scatter plots and things like that. So the first thing that we're going to need to do is plotting. Is import our plotting library. So the standard import for matplotlib is to import not all of matplotlib. Matplotlib is a very, I'll put a link to the matplotlib docs. And then over here. So matplotlib is one of the, probably the kind of canonical plotting library in Python. It was originally created, between 15 and 20 years ago as a library to port MATLAB-like plotting functionality into the Python ecosystem because there was nothing at the time. It's evolved quite a lot since then. The documentation is very good, very mature. There's lots of examples of plots that you could make. Usually when I want to make a plot, I come to this examples gallery and just kind of scroll through here and find something that is roughly what I want to do. And then I get the code to do that thing. And then I replace it with my own data or whatever it is I'm doing. So I will put the link. There's also a bunch of tutorials. So more tutorials on plotting with matplotlib, kind of as deep as you want to go. So I'll put the link to the matplotlib docs there. So this is the canonical import. We're just going to import the pyplot module. Typo again. There we go. Matplotlib.pyplot as plot. And now we'll refer to, our PLT will be the plot. That'll be the alias that we're going to use. So something really simple, if we did time, and so we just put some integer time indices and some positions, and I don't know, some positions, and then we could call plot.plot time positions. And indeed, so this error is basically saying that I'm trying to plot things that don't have the same length or shape. And that is indeed because I have 1, 2, 3, 4, 5 time positions and only 4 positions. So I'll put, so there we go. So always a good idea to label your axes. So you can do plot.x label, and then you can add an x label. So this would be time, maybe measured in seconds. And then a y label, and we could call this position measured in meters, something like that. And then we've got our labeled axes. We could put a title. Position versus time. We can make the font size larger. notice this just keeps coming up, and there's a couple of ways that you can suppress that if you find it annoying. So this is actually what is returned by, so each of these calls returns something. So in this case, the plot.plot returns a list of lines because there might be multiple line objects in the same plot. And then that's how you would get a hold of the lines if you wanted to do some more like customization of the lines or things like that. So whenever there's something, a method or a function returns a result that I don't care about, I like to just put an underscore equals in front of it. So I can just put underscore equals in front of all of these. And that basically just captures the all of these objects that I don't care about. You don't have to do that. It's just a thing that I do. Okay, so that's just kind of a simple examples, but actually we can do some plotting of Pandas data frames directly. So that's one of the cool things about Pandas data frames. So let's look at our, well, for plotting purposes, let's work with the Oceania data again. So I still have the Oceania data frame loaded already, but I will go ahead and put the code for loading that again. Okay. So simplest thing that we could do is, so there is a dot plot method, which I showed you earlier. So if we call this, we get something that's a bit nonsensical. But let's take a look through here and see what this has done. So by default, it's plotted a line for each column, and a line to Australia, and then presumably New Zealand over here. And it's just kind of connected the dot. So a dot between 10,039 and 10,556 here and here for 1952. So given that this is plotting one line per column, and the columns are the times, what we actually want to do is transpose the rows and columns and plot that. Because remember when we, so this is not what we want. But if we transpose this, and then call plot, that gives us what we want. So that's basically plotting the time series of Australia and New Zealand. Now, there's a couple of things that are, are not so great about this. One is that this is all garbled down here. And the reason that this is garbled is because the columns of this data are not really well named. So the columns, instead of being 1952, 1957, like integers, they're this string name, which is really unwieldy. So actually we can do a little bit of kind of pre-processing to get around that. So remember the columns attribute that we looked at earlier. So the columns attribute actually has a string, a method string that allows you to get access to the string representations of the column names and then perform string operations on them. But as a group instead of one at a time. So this avoids you having to do a loop. So for example, there's a strip method for strings that allows you to strip off text. So for example, if we strip out the GDP per cap, then this gets back an index where now we have these integers as strings. And there's actually another method as type that will allow us to cast it to an integer. And so now, in fact, we could just put 64 here, I think, if we wanted. And we could call this years. Now I'm just going to do the kind of like the method chaining version of this. Just line these guys up. This is more like the method chaining is calling dot this, dot that, dot the other methods, but the lining it up like this is more of an aesthetic thing, making your code more legible. So then what I'll do is now we will replace so here we've created these years, and now we're going to replace the columns with this new index that we've created. And that's a name error. And so now if we look at so now instead of the GDP per capita, we have the actual integer values for the years, which makes a lot more sense. It also makes for a prettier plot. Now, of course, instead of doing this pre-processing here in Pandas, if you controlled these raw data sets, like whatever process was used to create these raw data sets, then you might say, okay, well, I'm going to change the script that creates these CSV files so that we don't put this GDP per capita and underscore bit in there to begin with, and then we don't have to do that. But if this was the raw data that you had, it's generally a good idea to never edit your raw data files. Your raw data file should be treated as like a sacred text that you store and back up, but not and never edit. So like you read only from raw data files and write never. So that way you can do any kind of this processing that you need to do in your scripts. And then of course you can control your scripts and things like that. So that's just good kind of data hygiene. Okay, so we did that. So there's lots of different kind of plot styles that you can do. So so what we've been working with is the default plotting style, but you can actually set style to, so there's a style called ggplot, which mimics a popular R plotting library's default styling. And so once you activate that, then the plotting kind of settings have been changed so that when you start making plots, they're going to look a little different. So now if we did plot a bar plot, it would look something like this. And again, we could add a dot. Actually, you can pass instead of manually calling plot.x label and plot.y label, you can actually pass these into the plot method itself, which is what I would typically do when I'm plotting with Pandas. So this would be GDP Capita. No, something like this. Okay. So there are many styles. I can't remember all the styles off the top of my head. So matplotlib styles. Let's see if this is it. Style definitions. So you can, here's classic. So fast, 538. So here's one that kind of mimics, there's a political science blog in the US that's called 538. So they have their own style that's been mimicked here in matplotlib. Here's the ggplot style. So this is the one that we were using. There's another plotting library called Seaborn that has its own default setting. So you can have that within matplotlib by just switching to the Seaborn style. A lot of Seaborn themes in here. So Tableau has its own kind of style. So I'm not sure if these are all of them, but I'll put that link in the docs too. List of okay. So if we wanted, we could do some scatter plots. So if we wanted to do, whoops, a scatter plot. So I'm just going to comment that out for a minute. And then let's take a look at our data frame. So if we wanted to do a scatter plot of the GDP of Australia against the GDP of New Zealand, then we could do a plot with the kind of scatter, and then X, Australia, Y, New Zealand. New Zealand. Okay, so there's a scatter plot of Australia and New Zealand. Again, I'll just kind of pretty this up a little bit. Okay. So there is some more exercises for you to work on. So I'll set my timer again for about 5 minutes. And you guys are free to ask questions or just kind of take a few minutes to work on those exercises, and I'll just answer any kind of questions that you might have. So Salwa has a question about getting to install NumPy. So I would say the best thing to do would be just ignore it for now, and then you can come back later and launch a new binder. Okay, so I will launch some new binders now, and that will rebuild the repository software, the images. If you wait a few minutes until the binders are rebuilt, then actually, it looks like the public BinderHub. Oh, did I? Okay. So SciPy. So the public BinderHub is already refreshed and has SciPy on it. So if you wanted to jump over to that one, then SciPy is installed on that one. Otherwise, I don't really think it's worth it to go through the installation procedure again. You can take a look at it on the recording when it's out tomorrow if you want to walk through it again. Okay. Any questions about the plotting exercises? Is there any exercises that that you want me to go through? We want to go through together, or should I move on to the next episode? Okay, so there's a question about when do you think it's better to use Seaborn? It kind of, so plotting, it kind of just depends on which would you prefer to use. So like Matplotlib is so widely used that it's hard to kind of teach basic Python without showing you Matplotlib. Seaborn depends on Matplotlib, so basically it builds on top of Matplotlib a bunch of visualization. It tries to make it easier to do statistics-focused visualizations using Matplotlib, basically, is what Seaborn does. So in some sense, like maybe you could just start with Seaborn and you basically would be using Matplotlib underneath, but you might get some functionality with Seaborn that might make it easier for you to make the plots that you want to make, in which case you should just use Seaborn. So I guess that would be my answer. If you like the way the plots look in Seaborn, then start by using Seaborn straight away. Okay. Okay, so any other questions about plotting? If not, I'm going to move on to, we're going to take a slight detour and talk more about some Python standard library stuff. Okay, so what we're going to do now is we're going to move on to lists. So this is episode 11, lists. So I'm going to start sharing my screen again. Okay, so this is episode 11. We had some nice, interesting discussions, this morning, and we got kind of normally this is about where I would pick up just after lunch. So we're running a little bit behind today, but that's okay. like I said, the course materials and everything are online, so you can kind of continue to get through any episodes that we don't if we don't make it through everything today. So lists. So lists are a built-in data structure in Python for storing multiple values. And so we'll talk about examples of programs that need to collect values and some basic methods of working with lists. And then we're going to see an application of lists to data analysis in the next couple of episodes, once we cover for loops and then looping over data sets. Okay. So let's go over here. Lists. Okay, so a list is a data structure for storing multiple values. So a list could store multiple values of numbers. So you make a list by using square brackets. So this could be 0.273, 275. I'm just kind of making some numbers up that are kind of what was in the text. So we can define this list pressures, and then here, if we want to look at the list, and then we can use the length function, because like, just like strings, lists have a length, and so that will compute the number of elements in the list. You can index into lists just like strings. So if we want, we can index to get the first element in a list. We can use the negative indexing trick to get the last element in a list. You can actually replace an element in a list by assigning to that element. So if we wanted to change not the zeros, but the first element in the list to be 5, we could change it. And now this value has been updated. So the list, see, we've updated the data structure in place. There's some other methods for working with lists. So if we start with, we create a short list of primes. And then we can append an element to a list. So if we do primes append 7, and then we look at the list primes, we've added a new element to the list. You can combine two lists with another method called extend. So if we had primes was a list of 11, 13, 17, 19, and some more primes, 37, 41, 7. And then we can take our original list of primes and extend it by adding the teen primes. And notice that that's basically created, it hasn't created a new list. It's taken the original list primes and extended it with another list of values. Now, if we did, extend is different than append, because if we did the following, notice that this has not combined the list, but it's actually created a list whose last element is another list. So this is just to illustrate the difference between extend and append with lists. So we can use, there's a keyword delete, which will delete items from a list. So you could do primes -1, and then that will remove basically this last element from the list. So that removed the list. That was the last element of the primes list. So there is such a thing as an empty list. So empty list is just a list that contains no values. And this is useful in a programming pattern that we're going to see in a little bit called the accumulator pattern, where we start with an empty list and we accumulate values in the list by executing a for loop. And we're going to see how to process data sets using that kind of idea. So lists can contain different types of values. So you can create a list that has integers, that mixes integers and strings. So this is the example from the lecture notes. So, and that's what makes, that's one of the things that differentiates lists from other data structures, is that you can mix types. A list can create different types, basically. We saw this kind of earlier, but if you try to index beyond the end of a list, you'll get an index out of range. So something like the following doesn't work. Oops, and goals gives you an index out of range because the length of goals is 1, 2, 3, 4, 5. But the indexes for goals are 0, 1, 2, 3, and 4. So that would work. Let's select off the last element. Okay. So that was a quick kind of explanation of lists and some of the basic methods on lists. I just wanted, lists are a core data structure in Python. There's quite a lot that you could say about lists. I just want to introduce the basic ideas because I want to show you how to use lists to solve a practical data analysis problem. And so I've covered everything that I need to do that. So there are some exercises on lists down here at the bottom. So I'll set my timer again for 5 minutes and give you kind of some 5 minutes to go and take a look at those exercises and see if we have any questions in the chat. So the question in the chat is a bit of a technical question about when you append to a list, does it create new memory space and copy all the data? No, it does not. It uses only, it allocates only as much memory as is required to store the new item in the list and then kind of links it into the existing list. Well, I think what you have in mind playing is more like an array. So arrays have to be laid out in contiguous memory. And so if you needed to append an item to an array, then you probably would have to reallocate enough memory for the larger array and then copy all the data over to that other memory chunk and then release the old memory chunk. But that's not what is happening here. No, it does not. So the question was, does list does not use continuous memory address? No. So the list will have so all right. So now there's lots of questions coming in about lists. So So what is the difference between a list and a NumPy array? So a NumPy array is, so you should be using arrays if you're doing any kind of like scientific computing and numerical calculations, should be using arrays or something that's built on arrays, and it would be built on NumPy. So Pandas uses NumPy to efficiently work with all the numerical calculations that you're doing when you're doing data analysis. When you're working with SciPy to do like optimization or linear algebra or things like that, you're using NumPy arrays. They're optimized for that. Lists, so maybe like a use case for lists will become a little bit more clear when in the next episode, when we kind of go through a specific use case for lists. It's not that they're not necessarily slower than NumPy arrays. It just depends on what you're trying to use it for. So like you can, if you want to append an item to a list, then that's an operation that can be done in constant time with a Python list. But if you wanted to append an item to an array, that requires copying data. And even in NumPy, that's going to be slow because you've got to allocate more memory, you've got to copy data to append to an array, because an array requires continuous memory, a continuous block of memory. I mean, that's a very technical deep dive. So basically the answer is as to like which one is faster depends on what you're trying to do. And part of doing good scientific computational work, not just like data analysis, but good scientific computing in general, and part of the reason why if you're getting a computer science degree, you're going to learn a lot about algorithms and algorithmic complexity and data structures, is because you need to map the right data structure to your problem. That's what will that's one of the things that separates somebody who's had formal training in computer science with somebody who hasn't had that kind of training, is that usually a person with a formal training understands how to map data structures and algorithms to particular real world problems. And that saves time and money. And that's why, ideally that's why people at Facebook and Google and Amazon and places like that get paid a lot of money. Okay. So I'm going to take, is this a good time to take a break? Let's see. Okay, so let's take a 10-minute break and come back at 3:30, and then we'll kind of push through to the end of the day. We're going to cover for loops, and we're going to cover looping over data sets for sure. And then we'll see what else we can fit in. Okay, so we'll be back in 10 minutes. Okay, we're back. So probably one last big push through to the end of the day. Get my lecture notes up here. Okay. All right, so we are going to pick up some lists. Now we're going to do okay, so we did lists, so now we're going to do for loops. And then we're going to, we'll just plow on through. Okay, so for loops. So in this episode, we're going to see how to do for loops in Python. So I guess the good news is that if you've done for loops in any other language, it's going to be very much the same. All of the same basic ideas of a for loop are kind of, reach across boundaries between programming languages. They're basically the same. The syntax might be a little different, but the concept is the same. We're going to talk about what for loops are normally used for, and then we will talk about the accumulator pattern to aggregate value. So that's the big takeaway, is how to perform the accumulator pattern using for loops in Python for this episode. Okay. For loops. Okay, so a for loop executes commands once for each value in some collection. And so what do I mean by that? So probably the easiest way is just by example. So we've got this keyword for, and then we'll have something called a loop variable. We can call that maybe I in some collection of things. So it could be numbers, could be strings, could be data sets, could be machine learning models, could be anything, any kind of data type collection. So let's just do a list of numbers, and then let's just print the number, or print I, rather. So we do this, it just prints 2, 3, 4. Nothing, nothing fancy. So the collection, so if I was to rewrite this maybe a little bit more clearly, so the collection is the values that we're going to loop over. So let's call this numbers. And then up here, numbers. And then instead of I, a better loop variable would be number. Print number. So this reads almost like English. So you define some numbers, and then for number in your collection of numbers, you print the number. So that's pretty self-explanatory as to what that loop is doing. So syntactically, in addition to this for keyword and the in keyword, the first line of a for loop must end in a colon. So you need this colon here. And then the second line of the for loop must be indented, typically by 4 white spaces. So that's what differentiates the body of the for loop from the code that might come after the for loop. So print this executes after the for loop finishes. So this for loop prints 2, 3, 4, and then once the for loop is done, only then does it start executing this this block. Whereas if you put a print statement here, so then this is another line in the block. So this executes after each iteration of the loop. And then this executes after the loop finishes. So you can see what happens here. So we print the number, and then we print this executes after each iteration of the loop. And then we print another number, and then again, and again, and then finally the last statement. Okay. So indentation is always meaningful in Python. So this is our first example maybe of that. But so you need to be careful about your indentation. You know, if you anything that you want to be in the body of the loop needs to be indented 4 spaces, basically. This loop variable, so this is the loop variable number. So you could call this anything you want. I mean, it could be X, it could be something crazy like dolphin. But, don't do that. Just use something simple. And that is meaningful within the context of what you're doing. So if you're looping over numbers, the loop variable could be a number. If you're looping over data sets, the loop variable could be a data set. If you're looping over file paths, the loop variable could be a file path. So that's a very common common thing that you'll see. So loop bodies can contain multiple statements. So if we had some prime numbers, 2, 3, 5, 7, 11, and then we had a loop variable for prime and primes, then we did squared is prime squared and cubed is prime cubed, and then we could do print prime squared cubed. And so then for each prime in the primes, these 3 lines of code will be executed. Square it, cube it, and then print out all 3 values, and then start the loop again. There's a shorthand to range over sequences of numbers because it's such a common thing to do. So for number in range from 0 up to 100, print the number. Maybe let's just go 0 to 10 just so it doesn't. So notice that this starts at 0, goes up to, but again doesn't include 10. So here the 0 is actually redundant. If you just put in the upper bound, it will assume that the lower bound is 0. You can also go backwards. So you could go from 0 to 10 by -1, I think this works. No, you got to put the other way around. So you could go from 10 to 0. There we go. If you wanted to count backwards. So that's handy. Okay, so the accumulator pattern. So if we wanted to compute the sum of a bunch of numbers, so we could do that as follows. So we could define total to be 0, and that's going to be our accumulator variable in the pattern. And then we could do for number in range, say 10, let's do the first 10 numbers. Total equals total plus number. And then at the end, we will print the total. And here, maybe we want to go from the first numbers from 1 up to, but not including 10. So we won't start at 0, we'll start counting at 1. Okay. Right. And similarly, so if we did, 1, we could check this by hand. 6, 7, 8, 9. Yeah, there we go. Even better is to use the famous formula that, is it Gauss? Somebody came up with it, where the sum of the first n digits is, so here n would be 9, I guess, and then n times n minus 1 over 2. 1, 2. Oh, sorry, n plus 1. Got the formula wrong. Okay, so that way we could check, if we wanted to keep making this bigger, So let's actually go ahead and set n up here. So n is 100, and we'll change that to n, and then I guess down here, we'll make this a big capital N. We'll get rid of that. And actually that's redundant, so we'll get rid of that. Okay. What have I done wrong with the formula? There we go. The formula includes the upper bound. So it goes from the formulas for 1 up to and including n. So I need to do n plus 1 to make sure that the code is doing the same thing. Okay, cool. So this is a nice example of where a good algorithm trumps good computing, because if you keep increasing this, so there's a handy IPython command called timeit. So this is going to run a little numerical experiment. Oh, shoot. Let's get rid of this print statement. So this is going to run a little numerical experiment and see how long it takes to run this code over and over and over and see how long it takes. And we could do the same thing here. So this for loop, of course, is as a linear algorithm. It's just kind of linearly going over the list of numbers and then adding, incrementing the total. So this, as you increase n, of course, the time to complete this is going to kind of proportionally increase. Whereas with, of course, the good formula, the better algorithm, this is a constant time algorithm. So no matter how long, how big you make n, this is going to be done in constant time. Whereas if you make this really big, what did I make this? 1,000,000. So, and the gap between these two is just going to grow, of course, because again, this is comparing a constant time algorithm versus a linear time algorithm. Anyway, it's a bit of an aside, but a nice way to show you this kind of timeit cell magic command, which you can use to run these little numerical experiments on timing code in your cells. Okay. So that was our first example of the accumulator pattern. So there are some more exercises. And you should take a few minutes and go over these exercises. Particularly make sure that you understand how the execution of for loops works. There's an exercise here about reversing a string if you want. But really the practice accumulating is the one that I would advise you to take a look at. So there are, because this is the pattern that we're going to use in the next episode to great effect when processing data sets. Or actually not in the next episode, but the one after that, after we do some conditionals. Okay, so I'll set my timer, and then it looks like there might be some questions in the chat. So let me put my timer going. Okay, and then let's see what kind of questions are in the chat. Okay, more comments. Okay, so if anybody has any questions about for loops, feel free to throw them my way. Otherwise, I will just sit here quietly and drink my tea. And give you a chance to work on these for loop exercises. Sure. So Huang has a question about these, what he was calling them macros, but the correct terminology is IPython magic commands. And sure, so I can say say something about those. So maybe I will let me share my screen. And I will just put in here a side on IPython magic commands. So there are a whole bunch of built-in magic commands. And I'll put this link in the notebook in a minute. But so just like when you're running within a Jupyter notebook, you're running using the IPython kernel. So each cell in a Jupyter notebook is kind of like its own little IPython kernel in some ways, or console. But all the consoles are connected. All the notebook cells are connected, right? So you can use these magic commands that are kind of a little mini language, a little extension of, because they're not valid Python. Like you can't use them in a standard Python interpreter, but you can use them in the IPython console, the IPython interpreter, or within Jupyter notebooks. So there's line magics. And so these line magics are magics that apply to one line of code. And then there are cell magics, which apply to a whole cell, multiple lines of code. And so you can go down here and you can just see there's quite a lot of them. So maybe we'll look at, so there's a lot of the magics are actually like bash commands. So allowing you to do things like change directory, or so there's a conda magic command for installing conda packages. There's also a pip magic command for installing pip packages. So if we come down here to cell magics, so there's cell magics where you can, within a Python notebook, you can type bash commands into a cell, like actual bash commands, using this bash cell magic. You can convert individual cells in Python or in a Jupyter notebook to different languages. Like if you wanted to write actually a cell with HTML or JavaScript or LaTeX or Markdown or Perl, these kinds of things, you can kind of mix them together. Of course, this requires, like, if you wanted to run a cell as Ruby, you would have to have Ruby installed in the environment in which you were going to run that cell. So this might be useful for like bioinformatics, genomics workloads that use like Ruby, Perl together with Python and other things. This would allow you to have an environment where you've installed all that software and then have one notebook where you could mix and match these kinds of languages. There is, where was the, timed. Okay, so there's a time which times the execution. So there's a time magic for that, and then there's a time it magic, which with 1% is a line magic, but with 2 is a cell magic. Okay, so yeah, so there's the docs on time it. So let me just do So I'm just going to put the link in here to IPython magic commands docs for later reference. Okay. So hopefully that answered your question. Okay, so there's a question about range. So range is, let's go up here. So where do we start using range? Okay, so range is not actually a list. It has its own special type, which is actually what's called a generator. And the reason for this is that is computational efficiency. So instead of, in earlier versions of Python, range of 10 basically would just be expanded out into, expanded out into that. And so it would, range of 10 in terms of memory usage would use the same amount of memory as this entire list. And for a small list, for a small range like this, it's not that big of a deal. But as you get into like larger and larger lists of things, the memory usage of storing the entire list just to loop over it is a bit prohibitive. So what range actually does is it's a generator which stores the current value and then the rule to get the next value. And so basically, a range then goes from having memory that is linear in the number of and the size of the list to being constant memory. So actually, you can force range to be a list by calling the list function on it, and that will make it return a list. So hopefully that answers your question. So it's an optimization for compute and memory reasons. Okay, cool. So moving on to conditionals. Okay, so conditionals is, these are like if-then statements or if, else if, else type statements. So how can we get programs to do different things for different data, and how to correctly write programs that use if and else statements and semper Boolean expressions? So this is kind of what we want to cover here. And then in the next episode, we're going to put these things together to cover how to process collections of data sets, basically. Okay, so let me get my notebook up and running. Conditions. Okay, so this is going to be an example of an if statement. So the if statement is going to have a bit of true-false logic that determines whether or not the block of code that's indented after the if statement will be executed or not. So for example, we could have mass is 3.54, and if mass is greater than 3, then print mass is large. Let's just do this. So if we execute this, of course, the value of mass is 3.54, which is greater than 3, so it prints the mass is large. Then if we did the same thing, but now we make mass 2.5, nothing happens, because of course 2.5 is not greater than 3, and so the block of code that is indented under the if statement does not execute. So you often see conditionals show up inside of loops. So we might have some collection of values of mass. Nice, 7.1. So we've got these values for mass and for mass and masses. So we're going to loop over these masses, and then we do like some kind of a check. So if the mass is greater than some threshold, maybe 3, we'll just use the same threshold as above, then we want to do something specific. In this case, we'll print out the mass is large. And so now this statement only ever the body of the if statement only ever gets executed if the value of the loop variable mass exceeds the threshold, which is 3 in this case. Okay. Now let's talk about the else statement. So it's often the case that you actually want to do something for every value that you're looping over, but you might want to do different things. So if the mass is greater than some threshold, then you're going to do something. In this case, just print a statement. Print the mass is large. Else, so if the condition is not true, then we want to do something else. In this case, we'll just print the mass is small. And so here we get a print statement that's executed for each value that mass takes. So there's 1, 2, 3, 4, 5 values, but the print statement is different each time depending on whether the Boolean condition is satisfied or not, whether mass greater than 3 is true or not. Okay. Now, in Python, there's a third keyword that you can use if you have more than 2 conditions, or you have more than 1 condition, I guess, and that's elif, which is short for else if. So basically, you can have, if the mass is greater than 3, or, well, let's do it like this. So if the mass is greater than 9, then the mass is huge. Elif, the mass is greater than 3, then we can print the mass is large, else the mass is small. So here, each value that mass takes is passed through this if, elif, else filter, and as soon as it trips one of the value or one of the conditions, then the body executes and then it jumps over the rest of the conditions. So for example, 3.54. So when mass is 3.54, you check is 3.54 greater than 9? No. Then you go to the elif statement. Is the mass greater than 3.5? 3.54 is greater than 3.0, or the 3.54 is greater than 3.0. So then we print this statement and skip the else clause and go back to the top of the loop and grab the next value, 2.07, and perform the same thing. So in this case, 2.07 is not greater than 9. It's not greater than 3. So it then executes the else. The mass is small and prints that, and so on. So for 9.22, it only ever looks here. So the first statement is true, so it executes that block. and then doesn't even check the other two conditions. It goes back to the top of the loop. And so that's the next section of the notes about conditions are tested once in order. So another example from the notes. Would be what would be another good example to show? So if we have some initial value for velocity, and then we could execute a for loop, say 10 times, and then you could maybe adjust the velocity up or down depending on whether it was deemed to be moving too fast or something like this. So basically you're evolving the values of your variables with a loop. So velocity greater than some threshold, say 20, then we would print velocity is too slow, and then we would increment the velocity. So we would, or sorry, velocity is too fast. And then we would velocity, say maybe reduce it a little bit. Else, then velocity could be too slow, and then we'll increment it a little bit. Something like this. And then afterwards, we could print final velocity and whatever the velocity is at that point. So if we execute this, the first time it goes through the loop, the velocity is 10, so it executes in the else. And then you add 10, you get 20. So 20 is not strictly greater than 20. So you add 20 again, and then you'll come through, and then you'll have 30 is greater than 20. So you subtract 5, and you kind of iterate along like this until eventually you converge to 20. And then at that point, you just kind of go back and forth, I suppose. So that's just another example of a for loop with some conditional logic. Another, an algorithm that algorithms like binary search or the bisection root finding algorithm have this kind of flavor to them. You iterate the algorithm for some predetermined max number of times, and then if your if your current value is below the solution, you do one thing. If it's above the solution, you do another thing. And once it gets within a certain tolerance, then you terminate the algorithm. So that that is kind of has this flavor as well. Okay. So there are some more exercises for you to kind of have a go with. So I'll give you some time, some 5 minutes or so, to just take a look at these exercises and see how you get on. This one, processing small files, is actually what we're going to look at in the next episode in some detail, basically. Okay, so just take 5 minutes is definitely not enough time for you to go through all these exercises. They're quite, some of them are quite involved, but you can just have a look at them and get a feel for how they are, and then come back to them maybe later if you want some more practice. Okay, any questions about like the basic ideas behind if, about conditionals, if statements, if else, if, elif, else, this kind of thing? So a question in the chat about about tabs versus spaces. Yeah, so most IDEs or text editors for writing Python will replace tabs with 4 spaces without even telling you. And that's what's going on here. If you have a script that has that has a mix of tabs and spaces, then you can usually do a find and replace on the tab character and replace it with 4 spaces or however many spaces you're using. But try not to get into that situation because it's a bit of a pain to do that kind of converting. But I should also say that what matters is the consistency. So most text editors replace tabs with spaces because that way there's a guarantee that all of your code is using spaces that you write with those IDEs. And the same in Jupyter Notebooks, they will replace tabs with spaces. But you can actually use any amount of indentation so long as it's consistent. So 2 spaces, 4 spaces, 8 spaces. 4 spaces is, you should probably just use 4 spaces because that's by far the most widely used convention in the Python community. Any other questions? Okay. So let me share my screen. Okay. So now I guess if there are no more questions about conditionals, I want to go to the next episode, which is going to expand out on this idea of using for loops and conditional logic to process data files. So let's do that now. So looping over data sets. So here we're going to see how to use the ideas that we've learned so far today to process multiple data sets. So this is a very common workflow that many people across a diverse range of fields here at Cal, and well, basically any place doing scientific computing or data analysis work, find themselves. They have lots of files, and I've seen some genomics and bioinformatics users that have millions of files, and they need to basically process these millions of files, and they need to do the same or similar things with each of these files, and they just want to automate that process. So like kind of that's the idea of what we're going to talk about in this episode. Okay. Okay. So let's have a simple example to start. So import pandas. So pandas is probably already imported, but just in case it isn't, we'll go ahead and import it. So a simple example. So suppose that we have some file names, and in our list of file names, we have data, Gapminder, GDP Africa, and then we have, what were some of the others? So we have Asia and Europe, I think, are three of them. So if we have these file names, and then we can use a for loop for file name in file names. So we have a list of file names, and we're going to process each file in these file names. And what we're going to do is we are going to read CSV. So we're going to read in this file name, and our index column is going to be country. And then we're just going to do something simple. So we're going to print df.head. Let's just do that. Okay. So let's just look and see what has happened here. So we went over each of these three file names. We used the pandas read CSV file to load it, and then we basically just printed the first 5 lines. So this is basically just kind of like checking that we're not getting any errors, that we're kind of getting the data files that we were expecting to get. So these are all African countries. Here's the Asian countries. And then here's our European countries that we looked at earlier. Okay, so that looks like it's doing kind of what we wanted. Now, how can we improve upon this? Well, the first thing to note is that let's suppose that instead of, I don't know, there's like 6 or 7 of these GDP CSV files in this data directory. Let's go and actually take a look. So there's a Gapminder all, and then there's 1, 2, 3, 4, 5 CSV files. So, I mean, you could manually write out the paths for all 5 of these. I mean, we've done 3 of them already, but what if you had, 100 or 1,000 or 1,000,000 of these files that you needed to process? Like, you wouldn't want to manually write them all out. Like, that would be very tedious and error prone. So fortunately, there's a better way. So actually, we can just delete, in a minute, we can delete all of that. So we're going to import a library from the standard Python standard library called glob. And glob is short for kind of a Unix term called globbing. And globbing is, what it means is matching a set of files that match a certain pattern. So it's a technique from Unix, from Bash, for grabbing files that match a certain pattern. And you can use wildcard characters like a star to match 0 or more characters, or a question mark to match exactly 1 character. Other kinds of pattern matching functionalities are possible, but typically you don't need much more than that. So if we were to look at these file names, what's the pattern? So they all start with this. They all end with this. And then they all have some number of characters that change somewhere in here. So if we replace this with a star, then we have our pattern that we want to load all files that match this pattern. And then what we do is we use glob. The package has its main function, which is called glob, which takes in this pattern that we want to match. And now when we execute it, it will go through and grab all of the files that match that pattern. And so let's see. So here we have Oceania, and then, so this is Oceania, Australia, New Zealand, Argentina, Bolivia, Brazil. So this is the Americas. And then here's Europe, Asia, and finally Africa. So note that the order in which the files are returned is somewhat arbitrary. It's not like in alphabetical order. It's not in any particular order, right? So that's an important character. It's something that's important to keep track of. In many cases, it really shouldn't matter what the order of the files is in terms of the analysis that you're going to do. But if it does, then you should note with glob that what you should do is then sort the list. So for example, so let's look at file names. So file names, whoops, file names. So this is the list that's returned by glob. So this list could be in a somewhat arbitrary order. So if we wanted to make sure that it was returned, if we want to make sure that the loop processes files in a consistent order, then we should do sorted file names, and that will make sure that the file names are processed in a consistent order. And depending on what operating system you're on, OS or like Windows, Mac, or Linux, the ordering in which these files could be returned might be different. And so again, if you want a consistent ordering, then you should put sorted around it. So I'll do that now. Okay. So there we go. So now we'll get a consistent order of the, so I'll just put a note here. So use sorted if you need consistent ordering of file names to process. Okay. So now I've showed you how to use glob. Okay. And so let's see. There's a question in the chat. Okay. right, so now we're gonna, in the next kind of episode, now that we've seen kind of how to use glob, so this is an important, it's a small thing, but it's an important takeaway, because I see this kind of pattern save a lot of time for users here at Calst who have this kind of problem. They have a bunch of data files, they need to process them somehow, and glob is a good way to get a hold of the data files, and then you can process them using Pandas or NumPy or SciPy or whatever it is that you need to do that job. But just this pattern is useful. Okay. Okay, so questions about that? Okay, so if there are no questions about that, then I just want to move on to the next section, which is on writing functions. As writing functions is a very important important thing to know how to do. So I'll stop sharing my screen just for a minute, and then we'll jump over to writing functions. And let's see. Okay. So probably writing functions, this episode that we're about to start right now is probably going to be the last one that we'll cover today. And then I want to end with some time for Q&A and also point you into some directions for so that you can continue kind of building your Python skills. Okay, so writing functions. So I'm going to teach you how to write your own functions. So this is a major kind of learning outcome for getting started with Python. So we'll talk about basically the syntax of writing functions, and then the basic idea of that you should try to have a large number of relatively small functions that do one thing and one thing well. It's like a basic principle of functions. Okay. So writing functions. Okay. So the idea with functions is that they're whether it's Python or any other language, a function is how you take a large program and break it down into small chunks that are easier to understand. So a program that is 1,000 lines of one giant script, basically, that just executes from top to bottom, can be very difficult to debug and understand as a human. Of course, the computer is just going to start at the top and just execute all the way until it gets to the bottom. But if it's not doing what you want it to do, then it can be very hard for you to debug that, because it's basically one giant block of code that has to execute. Whereas if you break that up into functions, if you understand how to write functions and how to break your program up into functions, then you might have, instead of 1,000 lines of code in one script, you might have, I don't know, 10 to 25 functions that you can chain together to accomplish your task. And then you can test each of those functions to figure out where your problem is. So this basic idea of breaking up large programs into smaller chunks, where each chunk is a function, is an important kind of basic principle of programming. So just some semantic or syntax for writing functions. So the keyword to define a function is def, followed by the name of your function. So we'll just start with print a greeting. And then inside the function, so notice that the function ends with a colon, and then also the body of the function is indented, just like a for loop or a conditional block. And then inside the function, we'll write hello from inside function. So now when I execute the cell, the function definition is loaded into memory, but the function is not actually called, so there's nothing that gets printed. Whereas now if I do print greeting, now the body of the function is executed, and so the print statement is executed and it prints the output. Now notice what happens if you try to call the function without parentheses. So it basically just gives you back a string representation of the function definition. Doesn't do anything. So you actually need to, so you need the parentheses in order to call the function. So arguments provided in the function are matched, can be matched to, can be used in the body of the function. So if we have print the date, for example, and we have year, month, and day, then we can use these values in to create something inside the function. So for example, if we wanted to do the year and then a slash and then the month and then another slash and then the day. So we could then call this the date, and then we could print the date. Yeah. So now if we try to print the date, then we put in 2020, 10, and 20. So this works, it prints out the date. But what happens if we try to put integers in here? So that gives a type error. And that's because you're trying to, in the body of the function, our definition is not quite right. So we're trying to add an integer with a string, and so that doesn't work. So we could do a couple of things here. We could basically do something called, we could hint that people should only ever put a string in here, or probably a better way to go would be to convert anything that wasn't a string into a string using the string function. And then this would work fine. So you can pass arguments by position. So here I'm passing 2020, 10, and 20 by position. So I'm putting 2020 first, so it gets mapped to the year. 10 is the month, so it gets mapped to the month. And 20 is last, and so it gets mapped to the day. I could also pass by keyword. So I could do year, month, day, and that works. When you pass arguments by keyword, they don't necessarily have to be in order. So they could be like this, and you'll still get the right result. So that's a nice thing about passing arguments by keyword, is that you're guaranteed to get the right order. Because there's nothing in our function that would prevent you from doing something like this. So that gives you back something that is you know, I guess a valid American date, which, you know, month, day, year, but not necessarily the right format that we were expecting. Right, okay. So if you want to write a function that returns a result, then you use the return statement. So if we want to compute the average of a collection of values, then we could take the sum. So there's a built-in function for called sum to do the values, the total of values, and then divide by the length of values. And then we could return this. So that's a function that would, so the average of 1, 2, 3, 4, 5, 6, 3.5. So interestingly, what happens if you try to do this? So you get a division by 0 because the length of the empty list is 0. And so you'll get a 0 division error. So now you, as the person who's writing the function, has to decide, well, what should the behavior be if an empty list comes in? So if you decided that you didn't want to throw an error, you could do some kind of a check and say, well, you know, if the length of values is 0, then what should this function return? You could say, you know, result is none. And then else result is that. And then at the end, we return the result. So that would be one way that you could do it. There are many other ways that you could write this function. The point is that you as the person who's writing the function has to make the decision about how you want this to behave. Personally, I am somewhat biased towards allowing the 0 division error to be thrown, and then force. If you allow the 0 division error to be thrown, then you basically force the person who's using the code to figure out how to handle this case, which forces them to think about what they want to happen in the event that you get division by 0, because usually divide by 0 probably means that this data is corrupt in some sense. So you kind of have to think about these cases when you're writing library code and when you're writing functions about, well, what should be the case if I get, you know, bad data? If I have bad data that's passing through my program, I want to find out as soon as possible because it probably means there's a mistake somewhere else. So I would probably propagate this 0 division error rather than try to catch it with an if statement. But you know, it kind of depends on what you're trying to do. Right. Okay. So there is, okay, so that's basically all of that's the basics of functions. So we covered the syntax, we showed some examples. There are quite a number of exercises, some really good exercises on functions. In particular, this one I think is pretty cool. Simulating a dynamical system with a logistic map in Python. So this one covers functions. It covers for loops. It covers you know, an interesting numerical example with chaotic dynamics and a simple one-dimensional dynamical system. So a lot of interesting stuff in there, plotting some results, things like that. So I would highly recommend you, this would be a good exercise to kind of test how much you learned today. So if you can do this exercise without looking at the solution, then I feel like you picked up quite a lot from today. Okay, so that's all I want to cover. I want to leave about whatever time we have left for you guys to ask questions. And I also want to point you where to go to learn more. So why don't I do that, and then we can have questions. And actually, I have put this in this old notebook, so I will just copy. Okay. So this was the notebook from the session earlier this semester. So you can go back, if you wanted to look at that, you could see the stuff that I did, which is similar, but maybe a little bit different. So this, oh. Is what I wanted. Okay, so there are two books that I kind of drive users towards for where to go next to learn more about data analysis in Python. And the first one is the book by Wes McKinney, who was the original creator of Pandas, and it has it's the second edition of the book. So these are all the notebooks for the second edition that shows you how to do all of the code or all of the exercises and things that were that are covered in his book. And again, like the book you can get from, if you're here at Calus, you can get it from the library, from their digital collection. Just log into library.calus.edu.sa and search for Python for data analysis. And you'll find that you can get a PDF copy or digital copy online that you can work through. I highly recommend it. The other is Machine Learning with Scikit-learn and TensorFlow. So this is another book whose second edition just came out late last year and covers all of the basics for doing classical machine learning using scikit-learn and up through Keras and TensorFlow for deep learning. And you can run it in Colab or Binder like we've been doing. And then they have all the notebooks here. Just a heads up, in November, I'm going to be kind of giving a high-level overview of machine learning and scikit-learn by covering only chapter 2 from this book. So we're going to walk through kind of an end-to-end problem of doing machine learning to predict housing prices from start to finish based around chapter 2, the material covered in chapter 2 of this book. That will be later in November. Dates have not been announced yet, but that registration links will be sent around. So my goal today was to provide you guys with enough knowledge and understanding that you could pick up either of these books and get started quickly. So you know how to use Jupyter Lab, you know how to use Jupyter Notebooks and Python scripts. You know all the basics of writing Python code. So you should be able to follow the material in these books without too much effort, at least to get started. Now they go into a lot more detail with a lot of advanced topics that obviously I didn't cover today, but just enough, I gave you enough knowledge to get started on either of these books. Okay. So any questions? about anything that we covered today, even including the morning session, or ways in which you think you might want to use Python in your research, but you don't know what packages or libraries would be most appropriate. So I could probably answer those questions and kind of push you in one direction or the other. Do you want to use GPUs? This kind of thing. I could help push you in one direction or the other. How to save the notebook as a script. Okay, so that's a good question. And it should be, just give me a moment. I've got to remind, I haven't done it in a while, so I have to remind myself how to do it. Sorry, just give me a minute. I've got to look. So that's a good question. So I will put an answer to that question in the notebook, and then there must be, because I feel like there should be a very easy way to do it. Let's. Okay. Huang is mentioning NB convert. Yeah, so that's the way that I knew how to do it, but I wasn't 100% sure that that was the easiest way to do it. And so I was trying to look and see if there was an easier, like a GUI way with Jupyter that you can do it. Yeah, Glendon, you look like you.
So I just, sorry for the delay. I went to check myself. I didn't have it open, but I know that in Jupyter Notebook, there's like a download option, but it looks like in the lab, there's an option under Export Notebook As, and I think you can go executable script, and I think that might be. That might be the one.
I didn't even see that. I was looking for. All right, so let me share my screen. So we'll do an experiment here, and see if we can get this to work. So I guess the first thing that that we should do is not try to convert our crazy notebook that we've been hacking around with this afternoon, but convert something that might actually run as a script. So in my notebooks directory, I'm going to create a new notebook, and Python 3. And so then I will call this, let me just check. Okay, good. I just wanted to make sure I was stopped sharing for a minute so I could check that I was still recording. So this is being recorded. Okay, so we'll call this notebook to export. And then in this notebook cell, we will, so first I'll create not a code cell, just something else. So I'll call this, test notebook conversion to script. So this is going to be some text cell that I want to not be executed when this notebook is run as a script. So, and then in here, we'll put some code that we actually do want to execute. So hello world. And of course, yeah, we'll execute as a script. And we'll save that. And then maybe I'll just do this again. So this is another text cell that should be ignored when run as a script. And then we'll put another print statement, 4 plus 4. So that should, and then just to demonstrate something, I will put result equals 42, and then I'll put result but without a print statement. And I think that this should demonstrate that when we run this as a script, even if I execute this cell, I get the result 42. But my suspicion is that when this is run as a script, the hello world should print and the 8 should be printed, but this cell will execute but will not actually print anything when you run it as a script. So we'll test this hypothesis. Okay. So I've saved my notebook, and then if I do file, export notebook as executable script, and this is going to export it outside of my, okay, so this is going to execute or export it kind of out of Jupyter Lab entirely, which is not really what I was hoping to do. I wonder why it wants to export it. Well, okay, so we'll do it the slightly more technical way. So let's clear this out, figure out where we are. So let's go to Introduction to Python, Notebooks, and there's a Jupyter, just a moment here. So there's a tool called NVConvert, which I think I have installed, which you can use. Let's see if I have installed it. Yep. Okay, so it comes with Jupyter. So you can use this tool to convert your notebooks to different things. And so for example, so here's script. So script is going to be what we want to convert to a Python script. So let's clear this out. Convert to script. And then the notebook that we want to convert to a script is the notebook to export. Okay. And so over here, so now we have this Python script. So then I'll create a Python console and see where I am. Okay, so now if I run this notebook to export Py, yeah, so there we get hello world and 8, but not, so notice it, because we had this in a print statement, it printed hello world. Because this was in a print statement, it printed the result 8. But because I did not put the print around result, when I ran the notebook as a script, it did not print 42. So that was what I was saying earlier about the importance of print scripts. Now, I went through that pretty fast, and I used a command line tool called nvconvert, which is installed when you install Jupyter Lab and things like that. But that was a good question. And I feel like there should be a simple kind of GUI way to do it within Jupyter Lab, but it must be hidden in the UI somewhere because I can't find it at the moment. But that would be the command line way to do it. And hopefully that you can walk through this recording slowly to figure out how that works. So another question, so Awad is asking, is it recommended to use Miniconda or Anaconda? I encourage you to download Miniconda and then use Conda to create and download all of the software that you want for your different projects. When people use Anaconda, I find they download Anaconda and it comes with everything. And so then they just have this like one mega environment of software that they install everything into, and it becomes very difficult for them to disentangle what packages are used and what versions are used on their individual projects, which over time makes their life really difficult. So I encourage people to install Miniconda, which comes with less and forces you to learn to use Conda more effectively to install your software. So there's more upfront effort on your part, but it pays off, believe me, in the long run, because if you go down the Anaconda route, you're going to very quickly get a system where you've installed everything into a single environment and you're having a hard time disentangling what is actually being used. And plus, when you update software, it's going to change versions of other packages, and it just kind of creates a lot of difficulty over time, as though what I've found personally. Okay, we're almost out of time. So any other questions? Okay, so when will the email for registration for machine learning in November be sent? Probably this week. I have registration for the next workshop on Conda, which is not next week, but the week after that. But I suspect that we're going to be sending out the registration emails later this week for the November machine learning ones so that we can get people registered. And they'll be sent out both here within CALS, but also to KFU PM and the Aramco group that we've been in touch with as well. So this week, hopefully. A workshop on, do we have plans for a workshop on PyTorch? So at present, there's no plans to provide a workshop on PyTorch. With these more advanced topics, it's hard to understand like where the needs of the bulk of the users are. Obviously, putting on workshops like this is quite time intensive on the part of the staff scientists in the core labs. And so we try to figure out basically like where are the bulk of the users. And so for these core topics, it's pretty clear like what we need to provide training on the core topics. But for the advanced topics, we're not really certain yet how many people would be interested. So I would encourage you, if PyTorch is something that you're interested in, on the feedback form for this workshop, there's a place where you can put that down. So be sure to list whether it's PyTorch or if there's anything else you'd like training in, be sure to list it, because at the end of each semester, we gather up everybody's responses and then try to figure out if there is an overwhelming number of people asking for something like PyTorch, then we can certainly think about it. Now, that said, so if you're looking for a good book on how to code in PyTorch, there are a couple of books that I could recommend. So just give me one moment. So So one would be, I'll start sharing my screen again. So practical deep learning for coders. So this is an excellent course that's put out by Jeremy Howard. And there's a new course is out just yesterday, brand new course. It uses a library called FastAI, which is kind of a high-level wrapper around PyTorch that tries to get you started as quickly as possible for applying deep learning. It's really well suited for people who want to use PyTorch to apply deep learning to solve particular science problems, particular applications. If you are interested or working on with a group that is developing their own algorithms, then FastAI might be too opinionated in terms of how they structure your deep learning applications for you. You might want something else, something with a little more control. But there's a book that goes along with this course that just came out, deep learning for FastAI, for coders with FastAI and PyTorch. So it just came out. It might be available on the KAUST, from the KAUST library's digital collection with O'Reilly, but I'm not entirely sure. I haven't checked. But I'll put that link here as well. So for PyTorch, again, for PyTorch, for scientific applications, I would recommend starting here, practical deep learning for coders. Oh, I just realized I did not send those links to everybody. Thanks, Reem. I didn't realize I just replied to you. So good. Those are good questions. Huang has a Huang has a technical question about variable scope. When objects are passed as arguments to a function, do they actually get copied in memory? No, they do not. So Huang, maybe that's okay. So basically, when you pass, everything in Python is mutable. So that's something to be aware of. That means it can be changed. There's very few things that are actually immutable in Python. There are some stuff, but very few things. So when you pass an object into a function, or it will not be copied unless it's copied within the body of the function itself, which sometimes library authors will do that, but not always. Exactly what you want to do in that respect depends, again, on your application. So there's no general answer to that question. Okay, how can I trace the execution of functions? So that is a good question. So it's a good question. So Reem, that's a good question about tracing the execution of functions that I don't have a quick answer to, unfortunately. So there is a debugger, and I will try to put some links to how to use the debugger in the information about the video when it goes on YouTube. So in the past videos, I've been putting a lot of links that people have asked for in the lectures and the information about the video. So I'll stick a link to how to use a tutorial on how to use the debugger, which I think will allow you to walk through the execution of functions. Okay. Okay, so we're just over time. So last chance for anybody who wants to ask any more questions. Okay. Well, hey, thank you guys very much for being here today. I know it was a long day, nearly 8 hours of instruction time. So thank you for sticking with it. And I hope you learned enough about Python that you can now start learning what you need to learn to apply it in your own work. So thanks for coming along. And I would like to say, thanks to the Binder team for providing the compute resources for those outside of KAUST participants today. And then thanks to my colleagues at the Research Computing and IT and KAUST IT who have put together the resources internally at KAUST to support the KAUST BinderHub here for KAUST participants. So again, thank you very much. And the recording should be up on YouTube later this evening or tomorrow. This morning's recording is already posted. So hopefully I can get this one up in short order as well. So, okay, so thank you very much. And maybe I'll see you again at a future data science tutorial. Bye now.